Let's spend some time taking a look at Table 8.3 in Chapter 8 in Stock and Watson, which reports the results of nonlinear regression models of test scores. So our outcome variable is the average test score in the district. We have 420 observations. And as is usual when looking at a regression table, the first thing we should do is look at the footnotes to better understand the table and make sure we read it correctly. So the regressions were estimated using the data on California school districts. Standard errors are given in parentheses under the coefficients, and p-values given in parentheses under the f-statistics. Individual coefficients are given 1 asterisk if they're significant at the 5% level, and 2 asterisks if they're significant at the 1% level. And we might first notice, since we're here at the bottom, we might first notice that the R square is pretty much the same across all specifications except for specification 3. So let's go and see what's different about specification 3 that the R square is so low. We have the student-teacher ratio entered, but we don't have English language learners. We don't have the percent eligible for free lunch. We don't have the income in the school district. So it's a stripped-down, non-linear version with just the student-teacher ratio, a dummy variable for the percent English language learners, and a dummy variable, for, an interaction term for the percent English language learners times the student-teacher ratio. And what we see here when we move to that specification is that none of the coefficients are significant, 1, 2, 3. None of them have any asterisks. They all have high standard errors. And so it's not surprising that the R square for that specification ends up being pretty low. It has very little explanatory power because where it's not including the main explanatory variables, which are school lunch, average district income, and percent English language learners, except for this this dummy of percent English language learners. So we see that that simple regression, that maybe student-teacher ratio is explaining a lot of the variation, and all we need to do is interact it with the percent English language learners to explain even more of the variation. We can handily say, well, that's probably not the case. The explanations explaining variation in test scores requires a lot more explanatory variables than that. Oops, sorry about that. I have to go through and erase these individually and go through here and also erase them. So that's taking a look at the R square and the footnote. While we're here again on the back page, the second half of the table, let's take a look at the F statistics for joint hypotheses. So row A gives us the F statistics for the student-teacher ratio and the square of the student-teacher ratio and the interaction of high English language learners with the student-teacher ratio and the square of the student-teacher ratio and the cube of the student-teacher ratio. And so we're testing the joint null hypothesis. The joint hypothesis that all of those together are equal to 0. That is, student-teacher ratio and its variance, its interaction terms, its square terms, don't have any explanatory power. And we see that in all cases we can reject that joint hypothesis. Student-teacher ratio does have explanatory power when we consider all the variance of it in the regression. So the F statistic is reasonably high, and the p-values are all less than 0.01. So in every case, we reject the null hypothesis that there's no that they're all equal to 0. A narrower joint null hypothesis is that just the coefficients on student-teacher ratio squared and student-teacher ratio cubed are equal to 0, and we can see that in these three regressions we reject that joint null hypothesis. And then finally, in the last column, we consider the joint null hypothesis that just the interaction terms of student-teacher ratio and high English language learner dummy variable, whether there's a lot of English language learners in the district, we see that we can also reject that joint null hypothesis, although we're getting pretty close to 0.05 here, right? So it doesn't look like student-teacher ratio interacted with high English language learners is doing that much in terms of explanatory power. So that's our additional kind of hypothesis test. Let's go back to our main interpretation of the coefficients. So we see that student-teacher ratio has a negative effect. It's sometimes significant, sometimes not significant. When we consider student-teacher ratio as a nonlinear function, we see that it's a positive first coefficient, a negative second coefficient, and the third coefficient is positive. So we have a nonlinear relationship, kind of a more complex curvy relationship. So holding everything else constant, here's the student-teacher ratio, and here's the test score, right? And we have a relationship that kind of looks like that. I actually haven't put in the coefficients, so I'm just pointing out the generic form. You can always type in curve and then the syntax for curve to see what these numbers, when you put them in, what they actually look like in R, what the graph actually looks like. And you should do that to get a sense of what numbers like this mean for what the curvilinear relationship actually looks like, holding everything else constant. So you need to put in a number for the intercept in order to graph this curve and see what it looks like with these numbers. We notice that it's pretty robust across the three specifications where we have these squared and quadratic terms. The coefficients don't change too much, and when we look at the interaction terms of high English language learners times student-teacher ratio, we do see that it's somewhat different. They're significant at the 5% level in this specification. One asterisk here, remember, means at the 5% level. So you have to predict student-teacher ratio for a variety of you have to predict the test scores for a variety of student-teacher ratios, say a student-teacher ratio of 20 compared with 25 for high English language learner districts compared with non-high English language learner districts, in order to really see what these differences are looking like. Finally, we see that the eligible for school lunches is significant and negative, so pretty big effect there. And then our last coefficient is on the log of the average district income. So this is a linear log function. So remember, with a linear log function, we divide by 100, and then we interpret the coefficient as being how much a 1% change in income is associated with test score. So if we divide by 100, here we get 0.1. So a 1% change in income is associated with a 0.1 change in test score. More relevantly, sort of in the economic context, we'd say a 10% change in income is associated then with a 1 unit change in test score. Not a huge change in test scores from income, but statistically significant. A 50% change then is associated with a 5-point change in test scores.